and enthusiasm make this workshop possible. I am confident that SPECTROMAT 2026 will be a meaningful, enriching, and inspiring experience for everyone, fostering scientific curiosity, collaboration, and research excellence. Once again, I warmly welcome you all and wish you a highly productive and engaging workshop. Thank you.
Behind every successful academic endeavor is a visionary leader. I now invite our principal, Dr. Cincy Joseph, to deliver the inaugural address.
Good morning to all, respected dignitaries, teachers, researchers, and my dear students. On behalf of St. Stephen's College, Uravur, it is my honor to welcome you all in this conference, international conference, that is SPECTROMAT, which is the workshop on structural and spectroscopic tools for materials research, and organized by Department of Physics, St. Stephen's College, Uravur, in collaboration with Mahatma Gandhi University, co-sponsored by Kerala Science and Technology. Today, we all have gathered here for a common purpose, to share knowledge or to gain skill on tools like spectroscopic instruments. Actually, I have also used the spectroscopic tools during my research in 2000-2005 period. I used UV visible spectroscopy, atomic absorption spectroscopy, and also X-ray diffraction instrument also. However, this type of workshop, it is highly significant because science advances through collaboration and knowledge sharing. When experts, teachers, scholars, and young researchers come together on a common platform, learning becomes meaningful, dynamic, and inspiring. I'm confident that this program will strengthen research skills, enhance analytical thinking, and promote innovation among all participants. I wholeheartedly congratulate the Department of Physics, the Research Cell, and IQAC for organizing this timely and valuable workshop. The Department of Physics is highly active and vibrant, with dedicated faculty members contributing significantly to the research world through article publishing, peer reviewing, delivering resource talks, and organizing seminars and workshops. It is indeed a matter of great pride that the department is in the process of being upgraded as a research center in the near future. I also express my sincere gratitude to our sponsors and collaborators for their generous support and encouragement. I hope that these 2 days will be filled with insightful learning, meaningful discussions, and the generation of new ideas. May this workshop inspire all of you to explore deeper into the fascinating world of material science and contribute meaningfully to research and development. With great happiness and pride, I hereby declare SPECTROMAT 2026 is officially inaugurated. Thank you.
Thank you, ma'am. Moving into the core of our workshop, I invite Dr. Thomas Matthew, Head of the Department of Physics, to introduce our distinguished resource person for the first section.
Good morning, everyone. It is my privilege to introduce our resource person, Dr. Jemy James, Application and Support Engineer at Oxford Instruments, Bengaluru. Dr. James has over 14 years of experience spanning research, teaching, and industry. He has completed his PhD in photonics from the University of South Brittany, France, and has held research positions at premier institutions including IIT Bombay, IIT Madras, and Mahatma Gandhi University, with research contributions in photonics, nanomaterials, and optical characterizations. He has extensive hands-on experience in advanced microscopy and spectroscopy techniques and has supported numerous academic and industrial research laboratories across India. In his current role at Oxford Instruments, he is actively involved in application support, training, and implementation of advanced characterization techniques such as Raman Spectroscopy and atomic force microscopy. Today, he will deliver a lecture on correlation microscopy using Raman spectroscopy and atomic force microscopy. On behalf of the Department of Physics and Stephens College, I welcome Dr. Jemy James and invite him to deliver the talk. Thank you.
Thank you, Thomas, sir, for the nice introduction, and welcome you all for the workshop. So before we start the workshop, may I please, those who are present here, may I please know why you have come for this workshop? One of you can tell me why you have come for this workshop. What do you expect to gain from this? So it seems like that many of you are curious to understand the characterization techniques. I give you an overview of the one of the characterization techniques. I guess in the afternoon you will be learning more on the transmission electron microscopy. He's a one of the best transmission electron microscopists in India. So he'll be giving a talk in the afternoon at 2 o'clock, I guess. And then tomorrow also you've got distinguished lectures here. Okay, let's start. So I come from Oxford Instruments. Oxford Instruments was just a startup, just a research from University of Oxford in 1948. It was started, and then it slightly grown big. And I'm actually originally from Vitek. It was based in University of Ulm at Germany. So we were acquired by the Oxford Instruments in around 2022, and so we became part of the larger Oxford Instruments family. So this is a global footprint, and we have office in Bombay, but practically we are based in Bangalore, where we have got a demo machine is there. And these are the options for the Oxford Instruments, that there is plasma technology, magnetic resonance, nanoanalysis. Asylum is for the atomic force microscopy. VTech is the Raman spectroscopy part. Then you've got okay. Oh. And then Andor Science is for the cameras, the nanoscience and X-ray technology. There are a lot of things as such. Okay, so as you know, Raman spectroscopy was developed by Sir C.V. Raman and Dr. Sir K.S. Christian while they were doing a measurement in their laboratory at Indian Academy of Cultivation of Science in Calcutta. A quick question. Do you know when this Raman spectroscopy was discovered? February 20? Okay, so the first question that came to that. So I encourage you all to answer the question. So there are chocolates for you all. Okay, so actually the story behind Raman spectroscopy is that the story behind Raman spectroscopy is Raman spectroscopy is that Sir K.S. Krishna and Sir C.V. Raman was doing some experiments on in the month of February. The source of light was sunlight, and what happened is that Sir K.S. Krishna discovered something unique on that evening of 27th of February. So he ran ahead. Sir C.V. Raman was somewhere else. He ran and went to call Sir C.V. Raman. He was busy. He came back. By the time he came back, the sun had set. So they had to wait till the next day for the sun to rise, and thereby we have got the Raman discovery on February 28th. Thanks to the answer. Your good name? Asna. Good job. So these are the two people behind the Raman defect. So this is C.V. Raman, and that is Dr. K.S. Krishnan. So this is the Raman spectrograph in which they took the Raman spectrum initially. And if you go to Indian Academy of Cultivation of Science in Calcutta, you'll be able to see it. I happened to go there and 2-3 years ago, so we were able to capture it. It's still there. So I encourage you, when you're going for industrial visits or tours from your colleges and all, you can also go and visit Calcutta and see this Raman spectrometer. Okay, just quick introduction of the portfolio. Basically, we have got Raman AFM on the same machine, Raman SNOM. This stands for scanning near full optical microscopy. So, what does
നോക്കണൊക്കെ കൊടുക്കാതെ അച്ഛനുണ്ട് അത് കുഴപ്പമില്ല എസ്സിനെ നമുക്ക് രണ്ടാമത് ദിവസം നമുക്ക് ദിവസനെ പറഞ്ഞു ഒഴിവാക്കാം കുഴപ്പമില്ല അച്ഛനുണ്ടെങ്കിലേ
can somebody come here? ഇത് വെച്ച് പോയിന്റ് ചെയ്യാൻ പറ്റുമോ? അതിൽ പോയിന്റ് ചെയ്യാൻ പറ്റുമോ? ഓക്കെ, അല്ല ഓൺലൈൻ കൺവേർട്ട് കാണാൻ പറ്റുമോ? ഓക്കെ, മൗസ് ഇതിലേക്ക് ചെയ്യാവോ? അല്ലല്ല, ഇതിങ്ങനെ ക്ലിക്ക് ചെയ്താൽ സാറിന്റെ മൗസും ഉണ്ട്. So as you can see, this is most of you might have studied about spectroscopy, in which you're exciting a sample, you're getting emission on the same level. That is called as Rayleigh scattering. And when you're exciting a sample and you're getting an emission at a lower energy, it's called Stokes scattering. And when you're exciting a sample, when you're getting an emission at a still higher energy, it's called anti-Stokes scattering. So there is, when Raman will have Stokes as well as anti-Stokes scattering. Okay. So, and then along with that, you'll have got absorbance, fluorescence, and phosphorescence. These are the general methodologies which you will be coming across when you're doing Raman. So normally, most of the Raman will be having Stokes scattering. Okay, anti-Stokes will give you more information, but generally will be having Stokes scattering as such. So what is Raman scattering? So Raman scattering will take place only on the materials which are having asymmetric stretching. It will not happen for symmetric stretching. So when you're exciting a sample with an incident laser energy, the same energy can be transmitted out. It is called as Rayleigh scattering. You can see that lambda r is equal to lambda L. So excitation comes out. That is called Rayleigh scattering. Then you have got photoluminescence can also take place, which is not a good supporting material for the Raman scattering. Photoluminescence and Raman scattering are not so supportive together. Then you have got Stokes scattering, in which the wavelength will be different from the excitation. You have got also anti-Stokes Raman scattering. What can you learn about Raman scattering? So you are having a single frequency narrow line width laser. You should have a narrow line width laser to excite the sample. It will be exciting to a virtual energy state. From the virtual energy state, as it is unstable, it will be emitting out a scattered light. Either it can be of anti-Stokes, wherein the energy will be of higher energy, and then the second can be Stokes, where energy will be lower energy. So I hope, can you please raise your hands if anybody is there not from physics background? Okay, you're from chemistry background. Okay, but the chemistry, sorry to say, physics people, the chemistry people are going to be the benefactors of this Raman spectroscopy. You're going to enjoy more for Raman spectroscopy than physics people, even though the technology is more physics inclined, because the job market is so huge for chemistry people. Yeah. Okay. So for example, when you're looking at a molecule, you can see each of the molecule vibrates in a different orientation, right? Each of them vibrates in a different orientation. So each vibration is marked by each PS. So that's what we call as a fingerprint of materials. Fingerprints. So for example, if you're giving me a drop of saliva, we can understand whether you can have a cancer or not. A drop of saliva. That is a recent advancements of spectroscopy assays, specifically Raman spectroscopy. So recently, a month ago, a team from Bombay had come. They were working on spectroscopy technique in which they take the spectrum from saliva, then extract, sorry, they were working on blood actually. They take the spectrum from the blood, they remove the red blood cells and white blood cells, take the serum out of it, and from the serum, they'll be finding out a marker in the blood serum, which can predict whether you're going to have a cancer, or if you're having cancer, you can understand the state of the cancer, or they'll tell you, emergency, you should go and meet the doctor today itself. It's a company called Epigenetics in Bombay. So that is a significance or importance of Raman spectroscopy in today's life. Even though you might feel that Raman spectroscopy is an old technique, it is not like that. Just give me a minute. Yeah. So So we were speaking about the fingerprint, right? So each material, each bond will be having a fingerprint of it. So for example, the vibration of this can correspond to this particular peak. Vibration of this can correspond to this particular peak. The practical application for this is that, for example, you might have been learning about medicine and the medicine whole pharma industry. So you might be hearing that medicine from India is less attractive than medicines from Europe or something like that. For example, my father had cancer a couple of years ago. So during the final stages, we had to take a medicine from an Indian hospital. It was around 10,000, 15,000 rupees. But the efficacy of the medicine was not so great, so that the medicine didn't work well. Then we had to get a medicine from US. It was around 1 lakh or 1,25,000, something like that. That was much more effective to the cancer drug. Why can't we develop those drugs in India? So the people like you, chemistry people, basically, if you're doing a Raman spectrum of it, and if you're doing a Raman imaging of it, you'll be able to understand the changes in the Raman spectroscopic peaks from the materials as such. Thereby, you'll be able to find out what is the source of medicine, or what is the unique thing which makes those kinds of materials much more efficacy or much more efficient, so that it can be used. I hope some of you might be remembering a film called as Minnaram, in which the lead actor had some cancer, or the blood was coming from the nose, and you had a medicine coming in the airport, imported medicine, right? So why was that? Why couldn't India develop those things? So nowadays, what people in pharma industry does is that they take the medicine from outside. They the spectroscopy of it is one of the technique you can identify the components of it. What does it can give an information about the fingerprint, can give, as I told you, it can give an information about unique set of peaks that can be used to identify the molecules. What else can it give? It can give information of the functional groups. So the physics people, you can get the help from chemistry people to understand what is functional groups, how is functional groups playing a role in our daily life. Then the intensity of the Raman spectrum can give you information about the quantity or molecular concentration of the material. So if you're having a higher Raman peak, that means that you're having higher intensity in the materials, or higher concentration of the molecules, or higher concentration of the materials. I'm just giving an example. You might be having, suppose if you're having headache, you can go to the market and get paracetamol 500. You can also get paracetamol 600. And if you're doing the Raman spectroscopy of this paracetamol 600 and 500, you'll be able to understand that the 600 will be having a higher peak than this, because it's having more higher concentration. Then it can also give an information of the stress and strain in the bond. For example, as Raman spectrum shift in the peak positions can help us in understanding. This stress and strain will be very much important when you're talking about on-chip devices. So most of you will be having, I think almost all of you are having mobile phones here. The chip on your mobile phone some of you might be experiencing a problem that your phones are getting heated up. That heat is can get transmitted to your chip of your mobile phone, and the silicon channels on the sample can be extended, which can lead to your phone to be slowing down. Those stress on the silicon chip can be identified from the Raman spectrum also. That is, the peak will be shifting as such. And also next, you'll be able to also understand about the crystallinity of a material also. Anyway, you're having a class on XRD, right, tomorrow? But I'm not saying Raman will replace XRD, but it can give a direction or indication towards the crystallinity or amorphosity of the material also. Apart from this, you'll also be able to understand about the polymorphism of the material. So polymorphism is a way of crystal orientation in the sample. So these are multiple informations which you can get from Raman spectrum alone. Fingerprint, functional group detection, concentration, stress and strain, crystallinity, polymorphism, and crystal orientation. And then phase transition also is there. So a typical Raman spectrometer looks like this. When you're having an lasers, you need to have a source to excite the sample. You'll have a laser, you'll have a sample to be falling, you'll have a microscope objective to fall on the sample, then you need to have a spectrometer, and then you need to have a CCD, which collects the spectrum and gives the information about the spectrum message. So as I told you earlier, what does a Raman spectrum tells us? The band position intensity can give you information about the characteristics of the P, polarizability of the bond, detectability. All this can throw light in the fingerprint information of the molecules as such. What does the changes in the band, suppose, has anybody worked on, have you seen, so before I jump ahead, most of you, how many of you are PhD scholars here? Oh, you're PhD scholar, 2 of you PhD scholars, and rest of the them are master students. You are master students, right? Okay, you're all master students. Okay, so I hope you have heard of graphene, right? Have you graphene, carbon nanotubes, and all? So you've got D peak, G peak, and 2D peak. Physics people also might have heard. So D, G, and 2D peaks are there, and based on the ratios of the intensity of the D and G and D and 2D, you can classify whether it is a GO, graphene, or is it a graphite, and all those things. The ratio of the peaks. So the changes in the band intensity can give you information about the chemical structures also. For example, when you are nowadays, most of the vehicles are nowadays, there is something called as graphene coating. Or you might have been, suppose if you're watching TV, you will be seeing an advertisement of Suraj Venyarmod in Malayalam, it is Suraj Venyarmod. In Delhi, I think it is Akshay Kumar, somebody who's working on the advertisement for Asian Paints. They are talking about the graphene paints, right? Somebody might have seen bucket to bucket, something like that in Malayalam. So that means that you're incorporating graphene into the paint, so that they say that it is more dust proof, it lasts long, 15 years, and a lot of advantages are there. Though it is slightly costly, it's pretty costly. But people have introduced. So what is the role of how will you identify whether they have added graphene or not? So the graphene peak, the chemical changes in the band intensity can give you information about the chemical structures. So this is in fact, some of you might have learned about Beer-Lambert's law, right? In UV visual spectroscopy. Information can you get? We were approached by a company a couple of years ago. They were making silicons for the glass windows. How many of you are cooking in house? Do you have a pressure cooker in your house? Do you have a pressure cooker? So when did you last check the rubber beading or the rubber washer? Have you touched it? No. What about you? Have you checked there's a safety valve. Have you checked it out? Okay. If possible, those who are day scholars, please go home today. Go and ask your mother or a wife or whoever is there. Take the washer, the beading, or the circular ring around the pressure cooker and see whether it is flexible or not. If it is rigid, if it is not bending, go to market and change it actually. Okay, now that is a physics point of view. But what is the chemistry behind it? So as you are aging, as the material is undergoing heat and stress, the chemical bonds changes, and a bond, one of the particular bond will be shifting to another bond as such. So that is why after a year or so, you should change the ring, or you should also change the safety valve. So that's a practical application in our daily life. But the company wanted to identify what happens to the silicon when you're exposed to aging. For example, some of you might have come in an auto or a car or a bus, and all these things have wipers, the wipers in the glass, right? As you can see, in Kerala, the KSRTC buses or the government buses or the wipers can degrade over time, over a period of time. When we are exposing it to rain and heat. So what happens to the material? Why does it become degraded? You might have, if you touch an old wiper, it will be very rigid. A fresh wiper will be highly flexible. So the company wanted to understand the chemical changes. So what they did was they asked us to find out one particular peak, SiO, Si, and SiC, Si peaks, and they wanted to understand the changes in that particular peak before aging and after aging. So we were able to identify that one particular peak was shifting, thereby that peak was getting modified. So when that peak get modified, you can do our chemistry people can help us in understand the chemical structures, and you can do the necessary changes so that that particular peak doesn't get modified. So these are the advantages of using Raman spectroscopy to understand what is happening in physics as well as in chemistry. So thereby it can give you interaction of molecular interactions as such. And then while you are using a polarizer, physics people, you all might be knowing about polarization, right? Your physics, right? You've studied polarization, right? So when you're using polarized Raman spectroscopy, you can understand about the changes in the chemical structures and orientation of the crystals also. And then, as I told you, changes in the peak width can give you information about the crystallinity or whether the material is amorphous, whether there is any kind of defects and all of those things. Now coming into correlative microscopy. How many of you have you seen a microscope? Yes. No, normal microscope. You've seen a microscope, right? So the normal optical microscopy has a resolution limit of around 1 microns. The normal optical microscopy, which can be either dark field or bright field or fluorescence, or even polarized light microscopy. Nowadays we have got polarized light microscopes also. Then when you're talking about confocal microscopy, there is two sections of confocal microscopy. When you're talking about confocal microscopy, either there is confocal Raman or confocal fluorescence. So if there is any people who's in biology, maybe your principal ma'am might have used confocal microscopy in biology as such, confocal fluorescence microscopy. So we have seen people using the cells of the brain, cells of the heart and all. That is confocal fluorescence microscopy. And then what I'll be talking about is confocal Raman spectroscopy. So those two has a limit of around 320 nanometers, optical resolution limit. You can't beat that optical resolution limit. And then now you'll be talking about scanning electron microscopy. In the afternoon, my friend Manu will be coming over there. He'll be giving information about the scanning electron microscopy, which have a better resolution. Yeah, you can even go for angstrom level. Probably he'll show you the pictures of angstroms. While I was a student, he had shown me a bacteria being killed by a silver nanoparticle. I don't know whether he'll show it today or not. How a bacterial cell wall is broken by a silver nanoparticle as such. So each very informative information you can get from scanning electron microscopy. And beyond that, you should go for scanning probe microscopy. That is the atomic force microscopes. So I hope you have heard of atomic force microscopes. Are you from MG University? Okay. There is multiple atomic force microscopes. You should go and how many of you are from MG University? Okay. I recommend you tomorrow or maybe next Monday or Tuesday, go to the instrumentation division, see all these microscopes. There is optical microscopes is there in environmental science. Confocal Raman and AFM is there in the new building, and the new building towards your convergence. Yeah. And then electron microscopy is there in physics department. I request you to go and watch that machine and see how that works as such. Okay. And not only MG University students, all of you are requested to go and see. Maybe you can push up your teachers, take a tour to MG University, see all those machines and come back. And then also, when you're talking about correlative microscopy, what does correlation means? You have one microscopy technique over top of another microscopy technique. That is what is called as correlation. So normally, all of the microscopy will be having an optical microscopy as a base. You need to see the sample. So you'll be having optical microscopy. On top of the optical microscopy, you can build a bright field or a dark field, fluorescence or polarize. You can also correlate the whole microscopy with a scanning electron microscopy, which can give you information about EDS, energy dispersive spectroscopy, backscattered imaging and all. Also, the optical microscopy technique can be combined with a scanning probe microscopy, the AFM, atomic force microscopes. It can also be combined to an optical profilometry. So some of you might be using an Apple phone, right? So the Apple phone has a backside. So I know a person who sells a machine which is being used for the manufacturing of the Apple phone, wherein you have the standards for the flatness of your surface, the back surface of your Apple phone. I mean, the company has precision of the flatness. So for that, you need an optical profilometer to understand about the flatness. So apart from that, when you're talking about optical microscopy, you need to be correlate with the confocal microscopy also. Optical microscopy can be correlated with the confocal microscopy. I'll talk about correlative microscopy after the confocal microscopy after this. And the confocal, you can have multiple things. Fluorescence lifetime microscopy can be there. Photoluminescence can be there. Raman spectroscopy can be there. Second harmonic generation can be there. And then white light can also be there. So correlative, this is an example of correlative microscopy. Okay. So we focus a sample on a microscope, you get bright field, dark field, polarized light and all. And this is an optical microscopy where you are having, I guess all of you might have learned in your school days, 12th standard, wherein you have a light source, it's being collimated, you have a beam splitter, it falls down on using an objective lens, gets on the sample, gets back. You can use an eyepiece to focus a sample, and then to record the sample, you can use a camera. Basic principle. You have learned, all of you have learned this in your 12th standard. So this is, you're recording into the camera as such. So normally what happens when you're having a laser, light focus on a beam splitter, it falls on, it doesn't focus to a single point. It focuses to a slightly larger focal volume. So thereby, you can get information about the in focus material and out of focus material. Your sample will not be in focus when you're using the practically. So what can you do? You can introduce a aperture at the back end near the camera, wherein your out of focus rays are blocked and only the in focus rays are allowed to fall on the sample, on the camera. So thereby you will be able to resolve the material, or you will be able to resolve your sample, optically resolve the sample so that you can see the material clearly. So this is the whole simple principle of confocal microscopy. This is the whole concept used for confocal fluorescence and confocal Raman also. Then coming to Raman spectroscopy. Any doubts as of now? Anybody has any doubts? Okay. We are having, so when you are talking about Raman microscopy, you are having a laser, the source of energy. Laser is coupled to a microscope where it falls on the sample. It gets back and it falls on a spectrometer. And from the spectrometer, you've got the gratings and it falls on the CCD. So there is a light source, that is laser. Now coming to lasers. So who is doing PhD there? Are you doing PhD? What is your topic? What nanomaterials? Okay. Oh, fine. So if we are talking about explosives like TNT, you might be hearing RDX. In Kashmir, somebody has used RDX, terrorists RDX and all. You need to use 266 nanometer. That is deep UV spectroscopy is the best for understanding if you're talking about explosives. Suppose if you're using a graphic source for studying graphene or carbon. Suppose if you're anybody of you is working on 2D materials, then 633 is a good material for 2D materials. Suppose if anybody is working on biological samples, cells or cell membranes, RBC and all, 785 nanometer. The source of laser is most important factor when you are doing Raman spectroscopy. So if you're having an explosive material and if you go to a Raman spectrometer who's having 532 nanometer excitation, you may get spectrum, but it may not be the optimal spectrum. Before you go and do a measurement anywhere, you're having what is the excitation wavelength which you should use. Then go and find out the place where you are having the correct excitation. So this was the system I was installed yesterday. I just came today morning from IAC. So this was an system which was installed. So in IAC, so here you have a 785 nanometer laser, which is exciting sample. Also, you have another laser like 1064 nanometer laser. It falls on the sample, and the emission is second harmonic. You get a second harmonic emission, 532 nanometer, that is being imaged. So this is spectrometer, and yeah, this is whole system as such. And this is another system in Haryana where you're having two lasers. So there people have two options: either go for 532 or go for 785. So it's you can work on 2D materials, graphene, or biological materials. You can do imaging and all those. So choose the place where you have the ideal excitation wavelength before you go for the measurements as such. Now I'll go for some practical applications as such. So when you're doing, I told you about correlative microscopy, right? So this is a correlative image. So you do a Raman, so this is an AFM image and this is a Raman image, okay? Of the same sample on the same location. So what is the advantage? So you do an AFM image, you do a cross section, you draw a cross section across the line, and you'll be able to understand about the profile of the sample. And at the same point, you do a cross section of the Raman spectrum, you can understand about the intensity of the G band. So, for example, this is a graphene on silicon flake. You can understand how the intensity is distributed. So, both morphologically or graphically, and suppose you have developing a material tomorrow, you can go to an audience and say, this is my material, this is the topography, and this is the chemical intensity of it. So you can say, this is proof, this is chemically also there, and it is physically also there. I'll tell you an example. I hope, is there anybody who have not heard of MRF, Madras Rubber Factory? MRF tires? You've heard of it, right? So, most of you might be knowing that tires is having radial tires. Steel rods are inside it. I mean, it's not steel rods, steel threads are inside the tires. And MRF extracts rubber from Kottayam also for making their tires. But tomorrow, if anybody is having a rubber tree or latex in your house, if you go and dip a steel rod in a bucket of latex, it will not stick onto the rubber. The latex and steel cannot mingle together. So what you have to do, using some modifiers, you have to modify the material or chemical composition of the latex, and these modifiers link together. Okay. So in a simple tire of an auto rickshaw or of a bike or a lorry, there's more than 30 components inside it. It's not simple. 30 components are there. So each material has its own role to play when you're talking about double tire assets. So thereby, when you're doing an AFM topography and a Raman spectroscopy, you can correlate the chemically. Also, you can correlate topographically also. That is the power of correlative spectroscopy or correlative microscopy techniques as such. This is on polarization studies, in which this is more into carbon nanotubes. You're having an AFM image and then Raman measurement, so you can find out where the materials are located as such. And this is a prepared. So nowadays, any of you will be having a diamond ring, right? Nowadays, some of you, diamond has become much more cheaper because people are developing diamonds. They are making using CVD. People are developing diamonds. So we have a customer in Bangalore. Actually, they are from Gujarat. So they are making diamonds. Basically, the forefathers were customers of diamond. Now they are making diamonds using CVD. In the Bangalore Research and R&D Center itself, they have got around 10 CVDs in a line. They're working 24/7. They're making diamonds basically. What are they making diamonds? Earlier, diamonds was made for this jewelry aspect as such. You've got diamond rings, earrings, and a lot of things are there. But now diamonds are used for quantum technology. You might have heard, some of you might have heard of quantum technology, right? Quantum physics, quantum technology, and also you need diamond and envision this. You introduce a defect into the diamond using nitrogen vacancy and things like that. That will act as a single photon emission. Thereby, the single photon emission will be giving out will be helpful for the quantum communication, quantum technology and all, wherein you'll have a fast technology, fast communication, and some people are working on quantum encrypted signals from here to the satellite also. So there are many companies working on that. So coming back, so diamond is basically, this is a chemical vapor deposition made diamond. So these are lab grown diamonds. And something away from the spectroscopy technique, you people can get job in these companies, and they need people from MSc physics or MSc in chemistry. You can get good jobs in these companies. So coming back, so when you're talking about this, so if you're looking at the diamond signal, it has a typical Raman spec of around 1330, something like that, and then you've got fluorescence. So when you're correlating these two together, you'll be able to understand the material properties as such. So you've got the diamond, and you can also understand about some of the areas are more crystalline, where some of the areas are less crystalline. Okay. This is a Raman spectrum of a tungsten selenide sample, Raman image actually. So in the Raman image, and you can see each location has its own particular peaks. So I'm not jumping more into it. If you have questions, you can ask at a later point of time. Then this is basically a Raman image. Again, the previous one was a Raman image as a function of intensity. The first one is a function of one particular peak, how that particular peak is there. And this is also how a different particular peak is there. So it's slightly more complicated, but if you have doubts, I can explain it to you later point of time. Then we mentioned about correlative microscopy. The initial correlative microscopy I was talking about, AFM and Raman together. So this is optical and Raman together. So you have got an optical microscope of tungsten sulfide sample. Okay, this is an optical microscopic image. And then when you do a Raman spectrum, Raman imaging, you can correlate these two locations as such. So optical microscope and Raman, and then each color represents each particular peak. So those who are into research can understand the significance of each of these peaks. And then I'll wind up the PPT as soon as possible. There's something called as have you heard of carbon nanotubes? Yeah. So some people are trying to understand the distribution of carbon nanotubes on a biological cell. What they did was that they did an optical microscopy of the carbon nanotube imprints, optical microscopy. They did a Raman imaging. Say, for example, 200 points by 200 points. I mean, 200 points in the line and 200 lines in the image. So around 40,000 spectra they acquired. So they got like this. So this is a spectrum obtained. This corresponds to the cell as such, and this corresponds to the carbon nanotube. So can you see the blue locations here? So those are the distributions of the carbon nanotube inside the cell. So you get an image of a cell and you get an image of the carbon nanotubes. These are two separate images, right? But the correlative microscopy means you can combine these two together and understand how the carbon nanotubes are located in a sample. Thereby, you can understand how a material is transported inside a molecule or a bacteria or a cell as such. And this is what I was talking about, G band, 2D band of the carbon nanotubes. So I guess you people should go and study chemistry. Physics, the carbon nanotubes. You can understand about the 2D, G, and all things like that. And the chemistry people also can learn about this. Okay. Again, this is on rat epithelial cells, how they try to locate the sample. This each individual spectrum, each individual peak denotes a particular molecule. I'm not a biology person. Each say for example, nucleus, nucleoli, nuclear membrane, each can be identified from the Raman spectrum as such. And also you can look into the three-dimensional Raman imaging also. So this is one of the applications of Raman spectroscopy, in which they are trying to prepare some kind of energy from trash oil, cooking oil. They were trying to, so I'll not go much deeper into it. This was from the MG University itself. They were working on herbicides and they were trying on the effect of herbicides on the human cell, human serum albumin basically. This is one of the challenging projects which we had worked on. Because in the case of biological samples, you can't put higher energy into the sample. Because if you put, say, some of you might be is there any vegetarians in this room? Okay, one, okay. But still you have seen an egg, right? Egg white, when it is normal temperature, it is transparent, right? But if you're heating it, it becomes white, right? Or when you're making a bullseye or something like that, it changes its color, right? So protein get denaturized, right? Similarly, when you're trying to get spectrum, your protein get denaturized. Thereby, you'll not be able to get a true correct information from the sample. So then you're limited with the laser energy. So you can use only lower laser energy, and then you have to play around with the objective integration time and all those things. So this was a challenging sample. They did it, and the student got PhD after that. These are some of the possibilities. This is on that optical correlation basically. You people can. This is also has a person from Kerala, Abhijit MB. So you can see an optical microscopic image and then Raman spectroscopic image, and how so you got tungsten selenide one layer and the second layer on top of it, how this layer are twisted and layered on top of each other as it. So you'll be able to get a lot of information like that.
His love for nature, backed by an unquenchable thirst for questioning.
I just thought of showing you CV Raman, live CV Raman, just before the Raman Day or the National Science Day. And that's a Raman tree, which you can, if any of you are coming to ask your college teachers to arrange a trip to Bangalore, definitely your school trip or your college trip, what you call educational trip as such, definitely come to Raman Research Institute in Bangalore and Indian Institute of Science Bangalore. There you can, at RRI, you can find this Raman tree. It has been in the honor of C.V. Raman in RRI. Yeah. This is the time for questions. After this, we'll jump into some data analysis. I will be giving you information on the Raman, how we can do Raman data analysis and AFM data analysis. Okay. Any questions as of now? So, so I asked a question whether yes, whether we can combine atomic force microscopy and electron microscopy. As far as I know, with my very limited knowledge, atomic force microscopy can't be correlated because have anybody of you worked on AFMs? Okay. So AFM works on a principle you have in lights. Laser falls on a cantilever, it gets reflected back to the bottom photodiode. And yeah, in the next slide I will be showing. AFM tips, if it is moving like this, and if there is any kind of morphological structure, it will be deflecting and coming down. Assume that you're running on a very rough road in Kerala or somewhere, or super. The auto or bike will going like this, right? Same can be seen on the photodiode. For that, you need the cantilever, right? And an electron microscopic column needs vacuum. So the cantilever cannot be held in a vacuum. Yes, we have got Raman and electron microscopy together. Raman and electron microscopy can be combined together, in which you exactly. The story which I told you about the tires, radial tires, chemical combination, right? So the technique which sir has told is the ideal technique. You have a combined Raman and SEM. I mean, it was an SEM basically, FESEM, so that you can identify the chemical information, also the topography from the SEM also. I mean, information you'll get from FESEM. And also electron microscopy, you'll have EDS also. You'll get elemental information. So that is possible. That is really a hot topic these days. So we have supplied a machine in IT Kanpur, I guess, in the same. But Oxford EDS. But actinic force microscopy, I doubt whether we can combine with SEM thing because of the tip can fly off. That's why. Hello. Good. Join. Am I audible? Am I audible? Am I audible? Okay. Is the full screen visible? So basically we'll be having so basically, am I audible? Yeah. So basically we have got, when you're talking about any kind of spectrum, you might have something called as cosmic ray removal required. And then you might need something called as background subtraction. And then some of you might need to repair a spectrum as such. So, and then, so these are basic things which you will be needed. Cosmic ray removal, that can be because of the errors or some kind of error signals which is be coming up in the signal. Definitely you will need to have a background subtraction. You need to remove your background, and then you also would like to remove or repair a spectrum also. So that sometimes repairing a spectrum is not at all advisable all the time, but sometimes it is necessary. Okay. Now, so when you're talking about the single spectrum, you get a single spectrum, you can pass through the cosmic ray removal. So for example, in this case, this is you can see the small, I've highlighted with the blue boxes. Those are the cosmic rays in a spectrum. It will be, so those small, I've highlighted with the black, blue boxes. Those are the cosmic rays. So with the cosmic ray removal, you will be able to, so the upper one shows data with the cosmic rays. You can see those two are, the upper one shows the signal with the cosmic rays, and the lower one is the one with the cosmic rays removed. So that is the first thing which you should do with any kind of spectrum, whether there is any cosmic rays or not. I mean, they are accidental spectrum which will be evolved from the machine or something like that. So make sure that you do it out. Okay. And now coming to the, so this is the raw spectrum and this is the cosmic ray removed spectrum. Okay. Now coming, there will be, when you're talking about smoothing, some of you might be, have you started using smoothing in your spectrum? Not, oh, okay. So some of you you're doing, right? So smoothing also, there can be multiple algorithms in which you are trying to do your smoothing, but all of you has to be careful that you smoothen the data, that's well and good, but make sure that you don't kill your spectrum in the process of smoothing. Don't kill your spectrum in the process of smoothing. That is one of the foremost thing which you should take care of. So this software has some of these algorithms, whereas it depends on your requirements, what kind of algorithm we should use. For example, in the case of averaging, it uses some algorithms like average filter algorithm to smoothen it out. And then you can see in the spectrum that the average data has been, we can see the spectrum in which this was the raw spectrum and this is the average spectra as such. Okay. So that is first and foremost, if any kind of data processing, whatever you're doing, make sure that your spectrum is safe when you're doing a data processing. If you're not able to get a good and safe spectrum, try to rework the experiment or try to get a spectrum. Don't play around, try to smoothen it out and lose your data as such. Okay. Next is, this is another kind of algorithm called as median algorithm, in which it is also smoothened using median and then some skew. So it is Any machine will have its own algorithm to work on. So make sure that your spectrum is not smoothened. So for example, you can see a raw spectrum and a smoothened spectrum. So you're not manipulating the spectrum. But nowadays, when I go to my office in Germany, so they don't, this time onward, they are not using the smoothening algorithm this. Maybe they don't want to manipulate the data or something like that. They want to show the raw data. But at any cost, you don't play around with the data much. Okay. Then you need to remove the background of the data. Background subtraction is required because whenever you are having the inherent cost, the device or detector will have a noise level which is not at zero. Most of the spectrum will be, for example, in this case, the raw spectrum is coming around 600 counts. Why? Because none of our charge coupled devices can be made at 0 Kelvin. So this will be, most of them will be operating at room temperatures. And with this spectrum was taken at around minus 60 degrees Celsius. So the background or the baseline will be at around, in this case, this camera has around 600 CCD counts. So that is a background which has to be removed when you're presenting data. So make sure that you have to remove that background. So in this case, a background subtraction algorithm can be used. So there are multiple algorithms which can be used. For example, constant, minimum, polynomial, and all those things can be used to subtract the background. Okay. And then you can use, it depends. So polynomial can be used, constant can be used, then shape algorithm can be used. It depends on the algorithm of the system as such. So you can see the background has been subtracted while you carry it. So if possible, after your measurements, when you are presenting a data, make sure that you remove the noise from the cosmic rays or something like that. Make sure that you remove the background. That is the first and foremost things. And in the process, don't kill your data. So there is a give and take when you're smoothing out the materials as such. And then some of them want to normalize the data also. For example, if you're repetitively doing a measurement, say for a chemistry people, you're making a material with respect to different combinations, combination A, combination B, combination C, or you're varying the percentage of rubber or composites like that. So you'll have a particular peak which has to be normalized. Based on that, you're comparing it. So in that kind of scenarios, make sure that you're normalizing it. So you can also normalize the spectrum. So these are the pathways or ways in which you are carrying out the measurement. So cosmic ray removal can be done, smoothing can be done, background subtraction can be done, and finally normalization can be done. Then in some accidental cases, if you want to repair a spectrum, you can repair it, but it is not always encouraged repairing a spectrum, because repairing a spectrum can lead to a question of manipulation. So Adon sir has published a lot of papers, so he will be able to tell more than me on this aspect. So whenever if you are working on the material, when you are presenting the data, you will get questions from the reviewers. What is the raw data? Give me the raw data. So when you're giving the raw data and when you're showing the smoothened spectra and all those things, they'll ask you the validity of the data. So we should, only in very urgent cases, you should repair the spectra. Otherwise, you should present the spectrum just like that. So the upper one is the repaired spectra, and the lower one is the upper one is a non-repaired spectra, raw spectra. The lower one is the repaired spectra. And this one is for understanding about the components in the material. Suppose if any one of you is working on composites, composites means a material which will be having multiple components as such. For example, a tire is a composite of 30 materials, or anything like that. So you can understand about, for example, you can understand about the components present inside the spectrum as such. We'll work on it when we are working on the live sample. So I'll be showing you a spectrum of PET and PMMA composites together. Anusar, is this visible screen visible there also? Okay. So you can see so this is a spectrum which is obtained. So whenever you go to any machine, not even my machine, any other machines also, you get a spectrum as such. This spectrum, if you're looking at the information file, you can see this is around 150 by 150 pixels. I mean, it has been taken up 150. If you're looking at it, it has been taken with around 150 by 150 pixels. And yeah, so 150 points per line and 150 lines per image. So Raman spectroscopy, basically what you have to do is that you have to take a single spectrum. That is, a particular image you have to take, then you have to take a single spectrum. For example, if you're taking a spectrum from here, let's say you're taking a spectrum from here. You're taking a spectrum, you'll get a spectrum of plywood. If you're taking a spectrum from here, you'll get a spectrum of cardboard. If you're taking a spectrum, you'll get a spectrum of polymer. So these are single spectrums. But assume that I'm taking a line scan. That means you're taking a line scan, you'll be carrying out a spectrum in a straight line. Thereby, you'll be getting a profile wherein till here it'll be plywood, till then it'll be cardboard, then plywood, polymer and all. This will be very much useful when you're making devices or composites as such, multiple materials. If you're taking a profile, you'll be able to understand how a profile is, how your material has been deposited on a sample as such. So that was line scan. Assume that we are doing multiple line scans. Line scan, another line scan, another line scan. That is called as image scan, or that is what is called as Raman imaging. So this is a spectrum in which we have taken 150 points in one line and 150 lines in an image. So thereby 150 by 150 spectrum has been obtained. So if you're looking just like that, you'll just see as a simple thing. But if you're putting in a processing algorithm, so this is the material which was there. And then first step, what was the first step which I told you? Cosmic ray removal, right? So you wander around the sample and say, for example, at this particular point, can you see a cosmic ray? Which is a very sharp peak, like Dirac delta function. So these can arise due to the sample or due to the machine accidental data we can come. So cosmic ray removal has to be done first. For example, so there you at one particular point. See, can you see a cosmic ray? So that is one thing which you should remove at first. Okay, at any data. So in this case, I can remove it easily like this, extract. I can go for smoothing, graph smoothing. So this need not be on the software also. Any of the softwares, whatever you're doing, first you figure out whether there is any cosmic rays coming. Cosmic rays will be like a Dirac delta function, very sharp pulses. Try to remove it as it can come up as noise also. Then you go for smoothing. So I'm using this Savitsky-Golay algorithm. For example, I told you, no, we should not kill your data in the process of smoothing. So for example, you can see this average data. You can see at this, the green line is the clean data or smoothened data, and the red one is the raw data. Suppose if I'm using an extra higher values here, see, I'm killing my data, or my data intensity is coming down. So make sure that you don't lose your integrity of your data when you're working on the smoothing algorithms. So make sure that your data is safe and in the process of smoothing. Okay, so we extract, we go for background subtraction. So here you can see,
So here the starting level of the data is around from 280 counts, 280 CCD counts, right? So that means the 0 to 280 is the background. Then you have to remove the background. Are you getting? On the y-axis, you can see 280 is there, no? So you have to remove. So we can use this background subtraction algorithm. There are multiple algorithms available. In Origin also, I think we'll be able to carry out the background subtraction, but make sure that you do it background subtraction. And then you extract. Then you can either go to something called as true component analysis, or I'll show you individually also how to take the data. I extracted the data. So that data has been extracted. Now we need to understand how one particular material is being in the sample. So I put a filter. I put a summation filter. So there are multiple filters available. Like sum means it gives an intensity integration of the sum of the signals. That can give you information the quantity. During the first or third slide, we showed that higher the peak intensity, higher is the concentration. So some signal can be used. So this shows a particular combination of the particular distribution of the material inside it. But this is a 2-component system. So there is one more component. So the other component will be this one. So this is the second component. Whereas the first component is like this. So this is a PET and PMMA combination basically. So whatever kind of material you're having, find out the respective peaks of it. This is of PET and PMMA. Now I'll just show you about graphene and silicon, which will be easily relatable to you. So we got those two images. We extract it out. We can extract it out. So I can get this first image. I can get the second image. And then select these two. And you can lead it to image combination. So the first one was represented in red and second was represented in blue. So easily you can say that my PET in this particular domain and PMA is in another domain. So easily you can talk to your audience about that, how it has been chemically distributed. That is the beauty of Raman imaging as such. Then you can overlay this to an optical image. Unfortunately, I don't have the optical image over here. Now I'll show you one more data. This is a slightly bigger file. That is why it's taking some time. So this is a data, okay? The similar thing. The previous one was 150 by 150. This is 100 by 100. Did you understand what is 100 by 100? 100 points per line and 100 lines per image. So whenever you're carrying out a measurement, make sure that here you have a good resolution of your measurement. Otherwise, your sample will look, or a Raman image will look hazy. So similarly, the same process, cosmic ray removal. So for example, put it like this. So you can see a small speck over here, which is a cosmic ray. But you can see that this parameter didn't work for that. This parameter didn't work for that. It didn't remove this particular cosmic ray. So see, half of it is getting removed. Some of it is more is getting removed. Now, most of it has been removed, or majorly. See, when I put 0.9, I lost my data also. Okay, did you understand? I lost my data also here. So that is the tragedy if you're going for more data operation. So do your level best to be safer on your data in the process of data processing. Okay. So this NM factor 1 will not extract. We are going for smoothing. Anu sir, somebody is waiting at the lobby. So as previously mentioned, there is smoothing algorithm. So if you're wandering around your sample, you will see the peaks. Let us say we have used a value of 3 and 1 here. Let me put value of 9 there. So you can see my peak height is getting cut off here. My peak height. So this is what I was saying. Whenever you're playing around with the data, make sure that you're not killing your data. Then background subtraction. Extract. I'll put a representation of graphene. So does anybody know the peaks of graphene G peak value? Have you heard of graphene? You have heard, right? So it has G peak, E peak, and 2D peak. Okay. Your physics, right? Also, yes. Okay, so it has particular peak at D and G. So this is a spectrum. So if I put a marker over there, so 1586, G peak comes around 1585 and all. So you can, this is how the intensity of the 1586 peak is decorated in the sample, 1586. Whereas here, you're having 520 or 527, which is near to the silicon. So this is substrate silicon. And here it is graphene acid. When you're looking at the spectrum, you can see when you're clicking here, you get the substrate peak and the graphene peak, whereas here it is only the silicon peak or substrate peak. Okay. So you can make one spectrum for substrate. It'll look like this. And you make one filter for the graphene. The second image looks like this. So it's multiple layers of graphene. I'm not going much deeper into it. There is a lot of things which to go deeper into this one because of lack of time. I'm not going much deeper. So the first image represents the substrate. Second image represents the graphene. And here also you can see multiple layers of it, right? Can you, when you're looking at the spectrum, see how the intensity of the peaks are changing. Each are indicative of the layer structure or layers of the graphene as such. So we have got two images, we extract them, and then we can combine these two together. So you can easily tell to your audience, we didn't do much much processing on the graphene part. I just took one component as graphene. So my red is my substrate and blue is my graphene as such. Okay. Here also in the blue, we can see, we can go for single layer, multi-layer and all by observing closely on these layers as such. Okay. We are not going much deep because I have to talk to you about AFM data processing also. So we can simply tell to the audience, so this is my combined image where I have the substrate and the material together. This is how my substrate is distributed and this is how my sample is distributed, like that. Okay. Any questions as of now? Okay, I'll go back to the, so now we'll jump into the atomic force microscopy data processing. Have anybody done atomic force microscopy here? Okay. So all of you might have learned about atomic force, at least in your, are you PhD student? PG. Oh, you PhDs, right? Did you do a research methodology coursework? Not yet. Okay, fine. So you people know about atomic force microscopy, right? Okay, atomic force microscopy is used to understand the morphology of the material, or also it can also give you chemical information also. Now, unlike Raman, it can give you information the bonds also from there are multiple kinds of atomic force microscopy modes, contact mode and non-contact mode. Those are the simple techniques for any AFM. It will be like contact mode will be like you're almost touching on the sample and going, whereas non-contact mode will be at a particular distance from the sample. Those are the difference between contact mode and non-contact mode. Contact mode can give you information on the soft samples, whereas non-contact mode can give you information on the chemical information also, the samples also. Okay. There also we need something called as background subtraction. And those who are doing research, they might have got questions about statistics also of the, like, what is the noise level? Or what is the, yeah, we'll come into that. So background subtraction. So there are two kinds of background subtraction in an image, in an atomic force microscopy image. Either you can subtract the background in a form of a line, or you can subtract the background in the form of a shape. So there are two methodologies, shape algorithm and as a surface and line. So for example, this is a highly oriented pyrolytic graphene. And this is a blood cell. This raw Raman, sorry for confusing. So this is a raw atomic force microscope image of the HOPG. HOPG is highly oriented pyrolytic graphene. It's a very smooth sample. And the other one is a blood cells. So in this case, this is a raw image. And when you're doing a background subtraction, you're getting the layer by layer thickness of the HOPG. Whereas in the case of blood sample, when you're doing the background subtraction, line subtraction, you can see the RBCs in their own inherent forms. I hope you're understanding the difference. This is raw image. This is a background subtracted image. So all the cases, try to do a background subtraction in an AFM images. Okay. So here you can see the layers, and also there you can see the cells as such. The previous slide was I had used something called as line algorithm to remove the background subtraction. Now we'll understand about what a shape algorithm. This is gold wire, and when I did a surface subtraction, I was able to see the sample much more clearly and precisely when compared to the previous case. So the sample was seen much more clearly when we had employed surface subtraction. So what I would suggest you people is that employ the optimal method of background subtraction, which is suitable for your sample. It's not like one thing fits for all. One particular subtraction methodology may not be suitable for the other methodology. So make sure that you're understanding on the sample and employing the methodology for background subtraction. Then comes most important thing, image statistics for you. So once you subtract the background, there is something called as image statistics. For example, you'll get all these values over there, some standard deviation, median and all. These are actually very much important for your, reviewers will be asking you. So why this is practically important is that, for example, if anybody of you is going to be interested to work on biological materials, you might have heard of people making artificial dentures for your teeth or stent and all those things. You need to have surface to be oriented in such a way that there is roughness on the surface of the material so that the cells can come and adhere to the material as such. I mean, you need to have some particular roughness. It's not that all the materials in the world must be smooth. Some material has to be smooth, whereas some material has to be rough also. So you need to understand the roughness parameters. So people will be asking about the roughness parameters also. So these are the basic roughness parameters which people will be asking. This is irrespective of any kind of AFM. So first one is average roughness, SA. Second one is RMS roughness, SQ. Then third one is surface skewness and surface kurtosis. These are the basic values or basic questions people can ask for when anybody see an atomic force microscopy images. Okay, I'll explain to you each one by one. This is like an advertisement in the middle of a TV serial. So I think all of you might have brushed your teeth in the morning. Okay, so what was the color? What was the color of your brush? Black. What was the color of your brush? Huh? Purple. Okay, what was the color of your paste? Green. Green. Okay. What about you? White. White or red? Okay. I think you all might have had breakfast today morning. Has anybody had dosha today? You had dosha? Oh, was it a dosha like this? Okay. Plain dosha. But when you're looking into cross section, when you're looking into zoomed in image, was it a plain or was it having dentures? It was having folds, right? Okay. This is just like an interval or advertising break for you not to sleep. And you people might have seen this, right? Pineapple and jackfruit. It's most common in Kottayam and Thodupuzha and all those things, right? Let us look zoomed in. So you can see this is a zoomed in image of a pineapple. There's a zoomed in image of a jackfruit, right? Okay. Now coming back after a short break. Have those things in your mind, okay? Your black toothbrush, your purple toothbrush, your green toothpaste, and your white toothpaste. Okay. What does average roughness means? So whenever you're doing an atomic force microscopy image, average roughness and all these four parameters are much important as such. I'll give you what all these are standing for. Average roughness is one of the most important use parameters in when you're taking about atomic force microscope image. It's an arithmetic mean of the absolute coordinate. So Z position of the image, no, it's an arithmetic mean of the Z coordinates of the sample. So for example, if you are looking at the sample and if you are doing an arithmetic mean of the surface profile, you will get the average roughness. So that is one value which you should take care of. That is average roughness. So for here also you can see the average roughness of the material can be like this. Then comes RMS value, RMS roughness. It's usually some people call it as SQ, some notation it is an RQ. So it depends on the kind of, so when you're writing in a paper, the authors will be, the reviewers will be asking you what is a RQ value. Some will be asking you what is a SQ value. So it's called as a root mean squared value. It represents the standard deviation of the height distribution. It represents the standard deviation of the height distribution. That was the previous one was the average value. This is a standard deviation. Okay. Next is Qness. Some call this as RSK. Some reviewers will call as SKK. It depends on the kind of notations which is being used. But whatever it is called as Qness. So it gives an information about the symmetry of the profile. How symmetrical a profile is. That is what is useful for the skewness as such. So we learned about average roughness, RMS roughness, skewness. So anyway, I'll explain later. So RSK, the skewness positive means you are dominated by peaks, the first image. So you can see the peaks are more dominated. Skewness negative means you are dominated by valleys. Okay. Then kurtosis is also something. So some people call as SKU, some people call as RKU. It is a question of the quadratic value of the surface profile. So it shows the randomness of the height and the sharpness of the surface. So the first one is very sharp. The first image, first profile is very sharp. The second profile is very shallow. It is not sharp as such. So fundamentally, when you're looking at, one is very sharp and or it is perfectly random. The second one is less random. Anyway, this is the mathematics of it. I don't think you people might be needing it. So if you're looking at, so here you can see the skewness value. This is a random, this is completely oriented, but here you are having more valley-like patterns, whereas here you are having more peak-like patterns. Now looking the kurtosis values, here it is much more random. Here is much more sharper here. This is an average. It's almost randomness is uniform almost. Then, so we learned about background subtraction. We learned about the statistics. Now we have to, once you take a data, the third one is about the image cross-section. So what you have to do is that you have to, once you get an AFM image, you have to draw a line across the sample so that you get an image cross-section of the sample, which can indirectly give you the information about the height of the sample. Information about the height of the sample. For example, yesterday I was working on a 500 nanometer step height. So you need to make sure that your height has been confirmed by taking a cross-section of the sample, cross-section of the AFM image, okay? After background subtraction. Because before background subtraction, your sample can be tilted or like that. So there is a background as such. So you have to remove that one and then do the cross-section. For example, this is a background subtracted image of a sample, the same previous gold sample, which I've shown earlier. This was without background subtraction. And once you background subtracted, you can get the information much more clear. So that is the most important thing which you should do. Whenever you're doing to get an information from the sample, make sure that you do the initial preliminary data processing. Like in the case of Raman, it is be cosmic removal, background subtraction, and all. In the case of AFM, it is background subtraction and then cross section, all those things as such. So first you do subtraction, then you can carry out the measurement as such. Okay, so now looking at the valleys and peaks, you might understand that our pineapple had more valleys, whereas your jackfruit had more peaks. Your dosha had more valleys, where your toothbrush had more peaks, right? So kurtosis and skewness, you can remember about that. Okay, tomorrow morning when you brush, think about kurtosis, and when you're having dosha, think about the other thing. Okay, and when you're talking about the green toothpaste, think about the composites in your toothpaste. There will be multiple components in your toothpaste. Maybe you can do a Raman imaging of the toothpaste which you did. Okay. Okay. Now we'll just do a processing of a AFM data also. So this is an image of the AFM image in which you've got topography and phase. So probably this is a phase image will be obtained only when you're doing a non-contact mode. Phase image can also give you indirect information about the material properties also. So let us play around with the phase image. First, let's do the topography also. First, you can do a background subtraction. So you can see this image is without background subtraction and the upper image is after the background subtraction. So you can easily identify the differences or advantage of having the background subtracted image. So if I extract it out, so this is the three-dimensional rendering of the image as such. Okay, so hereby you will be able to understand how a material is really present. Okay, but now we'll look in the phase imaging also. Yeah, before that, I'll just show you one more thing. What is the importance of profiling? So on the same sample, we do an image cross section. I draw a line across this sample. So I can understand that this is around from 0, or this height is approximately 28 nanometers of the gold thing. So if you're looking at drawing a line across these two, you can understand each one has a slightly different height also. So, okay. And now we are talking about background subtraction one on the face image also. So this can give you information of the material property as such, face information. The topography will give you how it looks like, whereas face can give you information on the material property also. Okay, so with that, I'll stop it. So I'd like to conclude one thing, that atomic force microscopy and Raman spectroscopy are very much important in day-to-day life. And I would say the chemistry students and the physics students have a lot of potential for in the job market as such. And people are looking forward to have youngsters to work in Raman spectroscopy, atomic force microscopy as such, provided you learn the technique, you master the technique as such. Okay. For example, as I told you about diamond industry, people are looking forward to it. Paint industry, they're looking forward to it. Now, people are adding graphene into the cement. They're trying to make things better. Now, people are adding graphene into the tubes, which is being made. Tata Steel is working on that. Now, the MRF is making green tires. I mean, you might have heard of electric. If somebody of you is reading newspapers, you might be aware of the fact that the tires of the EV vehicles is not the same as tires of the normal vehicles. If you put a normal tire to an EV vehicle, that tire will get worn out very fast. So you need to have a special tire for the EV vehicle compared to that. So you need to develop a tire. Okay. So you need to find out components of it. And some of you might have heard about Chinese tires these days. Chinese tires are pretty cheap in the market. And you people are the research in arena wanted to understand how can they make these tires cheaper? So you need to have one of the techniques is Raman spectrum. You take the tire, you cut it into small piece, you do an atomic force microscopy of that, understand the components of it. You do a Raman image of it, you understand the components of it. Thereby, you can try to figure out how people are making things from outside, and then we can replicate the whole thing. So then again, in the case of, we have a customer in Chennai where they are working on oral cancers. So in the mouth, there are 4 possibilities for having a cancer. So on the cheek, on the teeth, on the palate, and on the bottom side of the palate. So all these places, if you are carrying out a spectroscope, you can easily find out. Oral cancers. I was at Tata Cancer Center last month in Bombay. It's not a good scene to go there. You'll be able to see people without the jaws as such. The jaw will be completely cut off. So they'll be looking like this as such. And we have seen small babies also there. So spectroscopy is one of the most beautiful technique. I'm not saying just like that because it's close to the National Science Day when Raman spectrum was discovered. It's one of the most beautiful technique having a lot of importance in your daily life. So for you people, I'm asking you for AFM information like your dosha or your paste and things like that so that you can remember AFM. The rest of the people, I ask you to go to your kitchen today evening, find out whether your rubber beading of your pressure cooker is fragile or is it flexible. Fragile or flexible. If it is fragile, replace it as soon as possible. Because I know a person who didn't replace it, the rice fell over. Then she accidentally walked on that place. She fell down. She had an ankle surgery. Ankle had fracture. She had a surgery and all those things like that. So you can also protect yourself. Being a science student, so you can go home, do some application. Okay. Okay. Yeah. Thank you very much then. There are n number of applications for Raman spectrum and all, but I'm not going beyond the because you people will be getting bored if you're going beyond the levels because each people will be using each kind of application. Pharma needs a different kind of approach. Steel requires a different kind of approach. So I've tried to talk in a level that you people can understand that. And I hope at least 5 people of you or 10 people of you will start using Raman spectroscopy and the atomic force microscopy soon. Thank you. Yes, sir. In the Raman spectrum, right? So in the Raman spectrum, right? Yeah. So what happens is that, so what does a detector working on? Detector converts optical signal into an electrical signal, right? Like any kind of sensor.
So you need a photon to fall on a sample that should initiate a conversion to an electron, right? So for that to take place, you have to have internal dark noise of the sample material. It's called dark noise, inherent noise of the material. So you might, what is your background, sir? Physics or chemistry? Physics. Oh, you're easy to explain. So you know the random motion of the materials, right? So electrons having random motion as such. Electrons will be moving randomly in the material as such, right? So in order to curtail the motion of the electrons and all, you need to cool it to a lower temperature. And you know that at 0 Kelvin, all of them come to a standstill, right? So nowadays the technology has been so much that the quantum devices and all is coming to work on two kinds of methodologies. One is cryo and one is in room temperature. So when you're working on room temperature, the random noises inside the sensors remain there. So my microscope cools down the machine to around minus 60 degrees Celsius using the Peltier cooling machine. If you're connecting a cryo system like liquid nitrogen, you can go to minus 180 degrees Celsius. Noise is much lower. And if you're using a liquid helium, 4 Kelvin, it will be much more lower. But again, technology wise, you need to have liquid helium plant and all those things. I'll just tell you an example. Earlier, my colleague who's working in plasma was telling that initially you had the gyroscopes. So it used to be of the size of a refrigerator. Initially, the first one. My colleagues, the Oxford was part of the initial development. But now, probably you're having a gyroscope in your phone. That is because of the on-chip advancements. So those are the technological advancements. Again, the quantum communication or quantum, now we are having the National Quantum Mission in which government is pumping around 2,000 crores of money. So there are two schools of thought. One is room temperature studies and one is quantum studies. So if you come across, so in case any of you are coming to Bangalore, I can show you some of the labs over there. We're working on this cryo systems and also room temperature studies, quantum studies and all of that. Yes, if you're coming to 0 Kelvin, you can come to 0, but at least you can reduce it off. Again, how does an AFM work? The laser, there's a laser, it falls on a cantilever and it falls on a quadrant photodiode. Quadrant photodiode is a diode which is having 4 quadrants. And the deflection of the AFM will be shown in the quadrant photodiode. So maybe probably it is falling here. Next one, it will be falling here. So it is also a sensor kind of thing, right? So that is also sensor. Ultimately, it's electronics, right? So you'll be able to, there are two aspects for it. One is you'll be able to understand the atomic layer precision. So my colleague has shown me, you have seen atoms, right? In textbooks. But I have seen in his machine. So you can see how an atom is represented using atomic force microscopy. So one is that one, and also it also depends on the interaction between the tip and the tip is basically a very narrow nanometer size tip, and the interaction between the atoms in the tip and the sample is what takes place here. So that is why it is called as atomic force microscopy. It's a non-destructive technique. I didn't go much deeper into it because it's a very beautiful subject.
Excitation. But when I identify for the spectrum that the error occurs in the spectrum is due to my wrong excitation wavelength. So what's the consequences?
Yeah, to an extent. You might have heard about curcumin, right? Turmeric. In Malayalam, it is called manjal, right? So people have been working on curcumin. It is having a lot of antibacterial effects and all, antimicrobial effects. So you might remember the sutures. When you have an accident or some stitch, people will be putting sutures, right? So it will be a polymeric material. And people are trying to decorate the polymeric material with this curcumin so that it is having the sutures the wound healing will take place much more faster. These sutures are polymers, biopolymers, whereas curcumin is a naturally formed material. Suppose if you're trying for Raman imaging of the sample or Raman spectroscopy of the sample, this using 532 nanometer laser, this curcumin will give you heavy fluorescence, wherein you will not be able to get a spectrum, or your Raman spectrum will be buried inside the curcumin spectrum, fluorescence. So you'll have to go for 785 nanometer laser. Suppose if you're going for explosives, the 532 may not work. So you'll have to go for DPUV system. So that is what you have to study, do a homework before you do the spectroscopy as such. Yeah. Thank you. We'll be able to see. I'll not say that I can replace a XRD, which is a we believe at the best crystallinity understand the crystallinity, but the Raman spectrum or the peak width can give you information, throw light into the crystallinity or non-crystallinity. From the Raman image, you can understand where it is much more better crystalline and less crystalline as such. It is not a quantitative method. Pardon? It's a relative value. To quantify it, you need to have a standard for it. Like any cases, suppose if you have a standard, then you have this one, then you can quantify it. Otherwise, you'll not be able to quantify. It's a qualitative methodology. Yeah. Because that crystallinity becomes very important. You might have heard about the drugs for the mentally sick patients. Those materials, if you're opening the tablets, it loses its efficacy. So that's why some of the medicines should not be, you might have seen some of the medicines coming in orange colored bottle, right? It should not be exposed to light because it's light sensitive. Some of the medicines, as soon as you open it, you should have it. Because when it is exposed to the atmosphere, it loses its orientation of the crystals inside the material. So those kinds of things you'll be able to understand. Moreover, from polarization also, polarization Raman spectrum, you'll be able to qualitatively understand how the crystallinity behavior is there also. Those possible, but I'll not say I can replace XRD, but this is possible. Yeah.
Excuse me, sir. We have a question from the online session. It is a question by Jasim. So he has told, thank you for your insightful talk. Could you please elaborate further on the role of spectroscopy techniques in oral cancer research, particularly in early detection, biomarker identification, and differentiation between benign and malignant lesions, and your experiences at Tata Cancer Center?
Is the student from Data Cancer Center? So for the good answer will be that just ask the student to look into Shovan Majumdar from Raja Ramana Center for Advanced Technology. They were actually the pioneers in this oral cancer detection. It was a Government of India Department of Atomic Energy lab. They used to develop this oral cancer probes in 2008, 9 and all. And Data Cancer Center was also working on it. So basically you insert a 785 nanometer laser using a probe in your mouth on the cheek. Basically the most easiest thing is cheek, or simplest thing is for you people is that the master student, whatever who is over here, you can coat a multiple layers of saliva on a silicon wafer or glass slide, and then you can carry out the Raman spectrum. So saliva is anyway coming from the mouth, right? So saliva can give you information about what is happening inside a mouth. So just to add to that oral cancer, recently I was in a company, they were working on, I was surprised to know, people who are eating bubble gum can have microplastics in your mouth from the bubble gum. So those can be identified from the saliva. Similarly, oral cancer also, the person can look into the papers from Dr. Murali Chilakapati at Tata Cancer Center. A lot of papers have been published. Or Dr. Shovan Majumdar from RRCat Indore. So they have developed a technology also. So that will be much more insightful. So benign cancer detection and this cancer marker detection, you can look into the company called Epigenetics in Bombay. They are working into this kind of technology in which markers and machine learning. So my advice to all the juniors, the master students who are here, don't forget about the present technology. Try to understand about Python, try to understand what is happening in AI, try to understand what is machine learning and all. So those are need to be linked to your physics or chemistry so that things will be much more easier. So those markers, identification of markers is being, what they do is that they capture multiple spectrum from thousands of people. They do machine learning and understand how the marker is being there. That is used to predict when a separate sample is given. That's how oral cancer and the marker identification is being carried out these days. Yeah, thank you.
We have one more question from the online session. It's by Asna Anwar. What kind of materials are the easiest to study using this, and which ones are the most difficult?
Materials, Raman active materials Raman active material is those materials whose vibrations in the molecules are asymmetric vibrations. Like, for example, you're having a water O, H and H. So provided your vibrations between the molecules is asymmetric, then only you will be able to get the polarizability, then only you will be able to get the Raman effect or Raman spectrum. If it is having a symmetric vibration, you will not be able to get it. So the first and foremost thing is asymmetric vibrations. Second is organic materials are the most easiest materials. But difficult materials are metals or elements alone, where it doesn't have any oxides or bonds as such. Then that is about the chemical material. Then from instrumentation point of view, when you're not having the proper laser to work on which, it will be difficult. For example, if I have a 532 nanometer laser and if I have biological cell, it might not be working because it will be giving huge fluorescence. So for this particular material, you need to have particular laser so that it is excited in the correct place. That's what. Thank you. If you have any more questions in the future also, you can talk to Adon sir. He'll be there. He's like my brother. So just let him know, we'll help you out, okay? And I hope you will be having a successful career in the field of science and technology. People like us need, yeah, please. Yeah. Yeah, each peak will be indicative of a functional group. Yeah, like so I was talking about those Viper, right? Do you remember when I was talking about Viper blade, right? So they were working on PDMS, polydimethoxysiloxane, in which it is having a combination of silicon and oxygen, SiO-Si bond and SiC-Si bonds. So they were trying to find out what happens to each bond with respect to the aging and all. Similarly, each functional group will have a fingerprint spectrum. So there you'll be able to find it out. Okay. How you're attaching. So if you give me an unknown, if you accidentally give me an unknown chemical, tomorrow if she's giving me her green toothpaste and if she gives me her white toothpaste, I'll be able to an extent, tell her what is the chemicals inside a toothpaste. Or one of you eats a bubble gum and then give me a saliva, I can to an extent find out what is the chemicals inside that bubble gum and what is the functional groups also. It is not a direct material, but we can throw information on the bottle with the probable functional groups. You'll have to cross check. Any technology is not independently standing alone. It should be complemented by other technologies.